Hello everyone, this is the lab number 5 diffraction, and today in this video we talk about the theory part of this lab. The objective of this lab is to study diffraction by using helium neon laser. So in this lab the laser we use is helium neon laser. Then we come to the theory part. Theory and equation used in this experiment. So first of all, about the theory, the definition of the light wave diffraction. Light travels in the straight line or with a smallest optical path length. However, when the light wave passes through a small window about the size of the light wavelength, so the size of the window is about the size of the light wavelength, then the light wave is bending around the edge and spread out. This phenomena is called light wave diffraction. As shown in figure 1, the helium neon laser passes through a single slit. As here, figure 1, this is figure 1, the helium neon laser, this is the laser source, passes through a single slit. Then this one is single slit. Width, and with the width A is the width of the single slit. This is A, at the distance L. So we'll have a magnet track. We put the laser on, then come laser to be the number 1. Then we put the slit at second one. After that, there will be a whiteboard to get the pattern of the diffraction pattern on this whiteboard. This one is number 3. Then, as the distance L, so L is the number 2 single slit, and number 3 whiteboard. Between the 2 and 3 distance L away from the slit, there is a diffraction pattern. The location of the dark area is defined as. So here the dark area, this is the diffraction patterns. The red one, it means bright fringe. This is a bright one. Okay, then there's some between the red one, there's a white space. Then that one is called dark fringe. Indeed, that part is dark. Then we only can get the red part as the red color fringe. So the location of the dark area, this is the black area, this one black area point out the dark area is defined as this function. A is the width of the single slit. Then sine theta, theta is the angle between, we give a line from the single slit to the center of the brightest fringe, central fringe. Okay, then here to here we give a line here, then another line is that from the single slit to the what exactly the one dark fringe we want. Then the theta between these two lines, then we'll give the angle theta. So for all of the dark fringe, indeed we give them the order. Go to the first one, the first dark fringe is m equal 1. Then m equal 1. So because we have two sides of the dark fringe, so we got 2 m equal 1 dark fringe. So 1 is here. I use m equal 1 here. And m equal 1 here. The dark fringe, we can talk about it later. Okay, so in this equation, a times sine theta equals to m lambda. Lambda is the wavelength of the light, this laser wavelength. So, and later on we have this is the equation we're talking about. Then after we got this equation. So when sine theta, right, and since the theta goes to 0, it's pretty small theta, we can do the approximation here. Sine theta approximately equals to tangent theta. Okay, so that's why we can approximately use here ym to L. Okay, this we use the approximation here. Okay, here we talk about the theta is an angle between an incident central propagation direction and the central minimum intensity of the diffraction pattern. Okay. Then order of the direction is m. Have order and integer value. Ym is the distance from the central minimum intensity to the central minimum intensity of the m order. Ym and lambda is the wavelength of the helium neon laser. So this is the wavelength of the helium neon laser in a very accurate number of the wavelengths. Okay. So then we talk about again about the Ym. What is the Ym? We're going in this lab. We're going to measure Y1 and Y2. Here we have we call whiteboard. And in the whiteboard, we will have the diffraction pattern like this in the lower figure 5.1. The middle part, this one, central pattern and central fringe. This is the brightest fringe, and then start from middle of this bright fringe to the first dark fringe. This distance is y equal 1. Okay, give y equal 1. Then how about y equal 2? So it should be the center of the right fringe to the second dark fringe. Then the distance between them, the r, y equals 2. So then that's why we call this is m is the diffraction order. Okay. So this is the order number 1. Then m equal 1 here. Then this is now m equal 2. That's why we have a several right here. Okay. So that's clear. So in this tab, in the experiment part 1, we're going to measure y1 and y2 for different size of the single slit. After that, now we come to the second page for the double slit. Just now we talk about single slit, right? Now we're talking about double slit. For the double slit, having slit distance d, So this one slit, okay, draw a bigger one here. For example, here is a board, and we have a double slit on the board. Okay, then the distance between these two slits, it's D. So that's the slit distance D, and there are diffraction and interference patterns on the screen shown in figure 5.2. Since the single slit width A is small, the diffraction pattern are wide. So it's very important sentence here. Since the single slit width A is small, so when A is small, diffraction pattern are wide. The interference pattern appears within diffraction patterns. Maximum intensity of the interference pattern is defined as. So the maximum intensity of the interference pattern defined as. This is the definition of the maximum intensity of the interference pattern. Then the minimum intensity is defined as this one. So this is like what we said, the bright fringe and the dark fringe. Okay. Then in this handout we call it maximum intensity and minimum intensity. Because you also have the order of the pattern. On the pattern, it also have the order. M could be equals to O, 0, plus minus 1, plus minus 2. So you can see. So now when we see this picture, first one is laser here. Okay, laser. Then there's a double slit. There's a whiteboard to get the pattern, interference pattern, and diffraction pattern. So for the double slit, we should consider about the interference pattern as well. Okay, so similar as the single slit case, we have diffraction patterns. Okay, then we can come to see here. This is the big one. The bigger one is they are the diffraction pattern. But in the diffraction pattern, but inside these diffraction patterns, there are some small. It looks like a spot, the bright spot, but it is several red circle, right? Then inside each diffraction pattern there are, we call interference patterns inside. And also the bright place is the maximum density, bright fringe of the interference pattern. Then the dark place between the two red circle, right between the two bright spot, it is the minimum intensity of the interference pattern, dark fringe of the interference pattern. And we also have the order about that, that is we define here. Then we come to the report part. Like what we did before, in this part I will introduce you what the report we have looks like. Then when you give me the report, when you hand in the report to me, then you only need to give this part, right? You don't need to give me the introduction part. Okay, your name, your ID, and we have three parts. Okay, part 1, use 2 single slits, study the diffraction by calculating the wavelengths of the helium neon laser. Okay, then plot the graph. Graph is between YM and L. And m equal to 1 and 2. So here we have two single slits. It's not double slits, okay? It's two single slits. We will do 2 times a measurement for one kind of single slit, which is here. We have the A, the width of the single slit, and we go to change. What is the difference is the L between the single slit and the whiteboard will extend the distance from 200 millimeter to 500 millimeter. Then you need to go to read on the ruler that the Y1, what is the length of the Y1 or the length of the Y2. Okay, there's a ruler prepared and you're going to read it. Then this is for the first round. Then second round we will change another single slit. Then after that you'll get four groups of the four groups of the data here. Okay. Then we come to part 2. Part 2 is about double slits. Okay. Then sketch the diffraction and interference patterns from 4 double slits. We'll have 4 double slits here at the same location L. So there's slit called A, B, C, and D. Slit width here. You can read from the double slit. I will show you the a picture about the slit. Then you can read from that slit. Slit width, distance between the slit, then the distance from the slit to screen. This is all fixed. Here is all fixed, and I have mentioned it in the experiment video. Now after that, you need to draw the pattern down. Okay, draw the patterns on the screen down to here. So for example, because you need to draw the one is diffraction pattern, one is interference pattern. What we said, okay, you need to draw. For example, you need to draw the diffraction pattern here, 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 here. It's like this, and after that you need to draw the interference pattern, right? Inside here, it should be like this, right? And draw it try your best. I want you to show me that what A and B, C and D, what they're different, okay? And they have also relation, maybe A and C, B and D, they are same long or not, or they have same number interference pattern or not. I want to show you. I want you to show me this one. So after that we go to part 3. Part 3 is that study the wave diffraction from the transmission grating. Transmission grating by calculating the wavelength of the helium neon laser. Then the maximum density of the diffraction pattern is defined as this one is for transmission grating. So before first one I introduce it is the maximum intensity here. Since it is maximum intensity, this means the brightest fringe. Okay. So second one, they have the order. The order of the diffraction, M is the diffraction order, but here it means for the bright spot. Okay, this is for M is the order of the bright spot. It doesn't like single slit and double slit. That's the dark spot, the dark fringe, which is the M order placed. But here is the bright spot. And the study okay, then we talk about the transmission grating. The transmission grating is that the first part one, there's only one slit on the board. Okay, part two, there are two slits on the board. Okay, when I draw this one, it means a slit. Okay, here means a slit. So this is long times ago. Maybe I think at least this is 200 years ago experiment. At that time, they only can do very thin, very small slit on the board. But nowadays the technology improves a lot, so we can do more slit on the board. We can do a lot of slit on the board, like this, a lot. So that is what the transmission grating. Okay. For this lab, what I do the experiment, I use the transmission grating, which is 80 lines per millimeter. So it means in the distance of 1 millimeter. Okay, maybe okay. This is 1 millimeter, right? This is the distance of the one. This is the distance of 1 millimeter. Okay, for this distance, there are for this distance. Okay, it's very short distance. Then there are 80 lines, 80 slits. Okay, we can think it is 80 slits inside inside the 1 millimeter. That is called the transmission grating. The good thing, the good part or advantage of the transmission grating is that they will give the fringe, they will give the pattern very clear. For example, this is a whiteboard. Then come to the fringe. When the transmission grating will give the fringe like this. So as similar like single slit, double slit, the middle part, the middle one is the brightest one, then be darker, but it will be give only you one spot, only one spot. There's no any longer fringe like this anymore. So that's pretty easy for us to go to measure it, go to measure the y1, y2, y3 like this. Okay. After that, so this is part 3. We're going in the experiment part. I've already tell you what is the L we use, and y1 I show you, and you need to go to read it. And just now I tell you, but I will mention it again in the experiment part video, and it's 80 lines per millimeter. Then after that, you use the formula, calculate what is the D. Okay, D and lambda. Lambda is this formula I give you, and lambda we only measure y1. So y1 here is m1 equals to 1. Then we do the approximation. Sine theta approximately equals to tangent theta when theta goes to 0. Then lambda equals to the as the formula I give you here. Then you need to write it down, your calculation, the process of your calculation. Then you get the wavelength of the neon laser. Then after that, you need to compare your result and with the experiment with result. Okay. After that, you need to write several sentences for your conclusion. Okay. So this is for all of the theory part. Thank you.